Welcome to my channel. I recently had the opportunity to record this lecture. It is extremely interesting and informative. It features Professor David Dilley. Topic: taking a walk through climate change.
So I'll give you a little refresher of what we are. I'm a former meteorologist, National Weather Service, and also United States Air Force. Currently, senior researcher, meteorologist, climatologist for Global Weather Oscillations Incorporated. 50 years experience. I don't know how that could be. I'm only 30 years old, but. And working partner with the International Hurricane Protection Association. I developed what is called climate pulse technology. And it's based on proven science. The Milankovitch cycles, you can Google it, you can find it online. It's electromagnetic interactions between the Earth, Moon, Sun. And I use the climate pulse technology for specializing in hurricane landfall predictions, El Nino predictions going out 2 years in advance, climate change, and weather cycles. Have an ebook on our website, and I have about 6 videos on YouTube and a couple on the website also. We're going to take quite a walk through climate change tonight, and from the very beginning of a lot of things we have forgotten about, and some new things tonight, very new. So it is true summers have become warmer. We've seen that. Even winter's warmer and hotter. Now that fosters thoughts of runaway global warming. Is that going to happen? Well, here's the proof of global warming. That's back in 1860 when it was very cold. That's what you wore for underwear. Then it got warmer, warmer, and warmer, and here we are in 2021. So that's the only proof for global warming. Will carbon dioxide and global warming end the world in 12 years? Will that happen? Okay, we're going to talk about carbon dioxide, a lot on carbon dioxide tonight. I'm really focusing on carbon dioxide and some climate cycles. First of all, the Earth's climate pulse. We as humans, we need a good night's sleep, or we just do not function very well. Well, the Earth is the same way. It needs a good, long sleep off and on, or it does not function well. So what controls it is the Earth-Moon-Sun interactions. This depiction is, there's the Sun, there's the Earth, and the Earth goes around the Sun in an elliptical path. Every 120,000 years or so, it goes out further away from the Sun. And because of that, and with the change in the axis, there we go, we get less sun, and we go into an ice age. That ice age will last for about 80,000 years, 60 to 80,000 years. But then we swing in close to the Sun. This happens about every 120,000 years, and we warm up. We're in a very warm interglacial period like we are now. And we're actually about 8,000 years off of the peak. So we're actually in a cooling down mode, coming away from the Sun. And this is what the cycles look like. Back 425,000 years ago, warmed up, very, very warm. Then it cooled down into a big, long ice age. And 325,000 years ago, very warm. 225,000 years ago, very warm. 150,000 years ago. And then just 8,000 years ago, we came out of a deep ice age, and There's our temperature way up. We're up where we're supposed to be. We're in an interglacial period. It's supposed to be warm. Now, we have shorter cycles also. Sometimes, especially when we get a little bit older, we need an afternoon nap, or else we don't function very well. Well, the Earth needs it also on shorter cycles. A little nap to refresh itself. So what comes into play here is the lunar cycle, the Earth, Moon, and Sun. And here's the Earth, the Moon, and there's the Earth. At this point, it's called what's called the apogee. This is an elliptical path also, where as it moves, the Moon goes around, comes in close, and then swings out further away. When it swings in close, you have more gravitational pull. And that's called a perigee, the close approach to the Earth. During a perigee, the gravitational pull, electromagnetic gravitational pull, increases by 30 to 40%. That's quite a bit, 30 to 40%. If you bring in the sun also, you get the Earth, Moon, Sun in alignment. Gravitational pull increases by 44 to 47%. This is why sometimes you see coastal ocean flooding without a storm. It's the strong gravitational tides. And the very strong gravitational pull, the full moon will go down to about minus 23 to 28 degrees below the equator. Then 8 years later, it'll be up above the equator. That's about an 8-9 year cycle. And the full moon, the new moon on the left side, is also just as strong as the full moon, believe it or not. So you have the two of them on strong cycles, and it acts like a plunger, pulling and tugging on the Earth's ocean's atmosphere and the inner core and outer core of the Earth. So what happens on very strong cycles? The outer core of the Earth can bulge 1.5 kilometers. That's quite a bit. That can cause increased earthquake activity, volcanic activity. And then we have a 72-year cycle, and we're going to be really focusing in on a 230-year cycle. So again, this is the depiction of the gravitational field as the sun goes down south of the equator and then back up north. That's 4-year cycles, 9-year cycles, 72-year cycles, and that 230-year cycle I'm going to be talking about. Now, these gravitational cycles are so important. People don't realize how important the moon is. If it was not for the moon keeping the Earth in its orbit, if we lost the moon, the Earth would lose its orbit. That's how powerful the moon is. And most scientists and the government is paying very little attention to these cycles. Now, that's what a cycle looks like over a course of 1,000 years. This is a 220 to 240 year cycle. You have a very strong cycle. 220 years later, it'll be strong again. 240 years, 240, 230 years. So it's about a 230, averages out about a 230 year cycle. That's what it looks like for very strong and weak cycles. Now, during the past 1,200 years, I showed you on an earlier slide, global warming cycles. They come every 230 years, about. Back in 850 AD, peak of the global warming cycle. 1050 AD, 1350, 1550, 1750, and now we're in a global warming cycle again. Now, if we overlay the gravitational cycles on top of it, what do we see? A perfect fit. A perfect fit. These cycles are caused by the interactions of the Earth, Moon, Sun. That's all there is to it. Now, carbon dioxide. Let's really home in on carbon dioxide now. Atmospheric concentrations. How CO2 is measured. And you're going to learn some things tonight no one else has seen. This is brand new, some of it. First of all, Earth's atmosphere, what makes it up? 78% of the atmosphere is what? Nitrogen. Who would know? A nitrogen, of all things. Nitrogen. Oxygen makes up only 21%. Argon, 0.9%. That's 99% of the atmosphere right there. If we add in water vapor is about 1%. And it's a greenhouse gas. So you add 99 plus 1, you have 100% of the atmosphere. So where's carbon dioxide for a greenhouse gas? Way over here at 0.02%. Almost too little to measure. So we have to measure carbon dioxide in a different way. Instead of percent, 0.02%, we have to blow up the figures so we can read it better. If we take a piece of air, just one little piece of air, and it has 1 million parts in it, has 1 million pieces of gases in it, okay? One piece of gas is 1 part per million, because there's 1 million parts. And this is what we're going to be doing in parts per million, because the percentage, 0.02, is too small. So now the air is made up of nitrogen, 780,000 parts per million. Oxygen, 2009. Argon, water vapor, 10,000 parts per million. So that's just about the total, 999,800 parts per million. That only leaves 250 for carbon dioxide. That's it. Now we look at that piece of air again. If we look at the greenhouse gases in it, that blue, that's water vapor, 10,000 parts per million. Little yellow dot is carbon dioxide. That's it. Now, how do we record carbon dioxide? We've only had instruments since 1860. So how do we know what happened prior to 1860? No instruments, so how was it done? Well, very non-precise, approximate readings. And I want to really say that again, non-precise, approximate readings. Everyone thinks these are etched in stone. They aren't. They're only approximate readings. They use tree rings for the past 1,000 years, tree rings and lake bottom sediment. Beyond 1,000 years, they use trapped air bubbles in gas. Trapped air bubbles in ice is what they use during the past 500,000 years. The little air bubbles get trapped in ice, and that little air bubble contains all the gases. And that's what they're looking for. So this is what we're going to look at now. Trapped ice in the Antarctic ice during the past 500,000 years. Down at Lake Vostok, that's where they drill their ice cores. They drill down to 15,588 feet. That's a lot of ice. Over 2 miles of ice. Ice at the bottom is 500,000 years old. So then they take, that's what an ice core looks like, then they take a slice out of that ice core. And you're going to have all kinds of air bubbles trapped in there that has your carbon dioxide, nitrogen, oxygen. So we can determine, or approximately determine, how much was in there in a very approximate time period. And the problem is, this ice, you get down in there 1,000 feet or what have you, and the ice is compacted so much, you can't tell 1 year from the other. You can't tell 100 years from a year or anything like that. So what they do, this slice will cover a time period of 1,000 to 4,000 years. That's a long time period, one slice. And once they analyze it, this is what they came up with. This is the temperature and carbon dioxide during the past 500,000 years. Over on the left, came out of a glacial period, warmed up. The red line is the temperatures back 450,000 years ago. Blue line is carbon dioxide. And they said the carbon dioxide was 280 parts per million at that time period. Then we go down into a deep, long glacial period. But you see the red line, you see the temperatures falling fast. Look at the carbon dioxide still up high. If carbon dioxide causes global warming, how did the temperatures fall? And that's what they tell us. The carbon dioxide causes the temperatures to rise. Tell me another one. So then, another warm period back 338,000 years ago. And then it cooled down, but look at the carbon dioxide up there, very high, 298 parts per million, and the temperature falling like a rock. It doesn't cause global warming. So there's another one, and we keep coming over here to present time. We came up, this was about 6,000, 7,000, 8,000 years ago right here. And then the data gets really jumbled up because you can't use ice that's newer than 5,000 years old. The air bubbles are not locked into the ice. So you can't use what they call new ice. So they did a lot of fudging during the past 5,000 years to try to come up with approximate data. And we're going to talk about this new ice on upcoming slides. And one thing they're saying is parts per million during this whole 400,000 year period peaked out at 280, 298, 278, 287, 265, and now we're up to 417. All of a sudden, 417. Well, why are these levels so low? Shouldn't they be up higher, maybe? We don't know. We're going to take a look at that right now. Ice core readings. As I said, they're not accurate and are misleading. And this is all new information that's coming now, the next several slides. There are 3 important corrections we're going to do to the ice core CO2 data. One, there's a group of physicists, they're coming out with a new research paper. I was honored to be a peer reviewer of the paper, so I know what's in it. And it's going to be published in a couple of months. It's approved for publishing. And so one thing I want to show here, okay, as we talk about it. This is their findings. I can't tell you everything on their findings because I'm kind of sealed on a couple of things. Hasn't been published yet. Carbon dioxide back in 1750 was 277 parts per million. 1800, 283. You see it went up a little bit. 1850 was 285. 1900, 296. And 1950 up to 311. So you can see a gradual increase on the carbon dioxide. Well, according to the research paper, instrument readings began in 1958 out in Hawaii on top of a mountain. All of a sudden, look what happened to the carbon dioxide. It was coming up slowly, then pew, bam. Only because we have instruments, or what happened here? They say it's from fossil fuel burning. But why did it start in only 1958 and come up? Well, the paper that's coming out, They're saying that the total rise in carbon dioxide since 1750 is only 77%. Industrial is 23%. So they're saying that most of the rise is natural. Natural, 77%. Industrial, 23%. So that kind of put off a light bulb in my thinking, where I had a lot of things on some of my previous talks, but I hadn't brought them all together. And now we're going to bring them together because it fits right in with their paper. And also they say only 12% of the total atmospheric CO2 concentrations is industrial fossil fuel. But total in the atmosphere, 12%. Far too little to cause climate change. Far too little. Okay, correction number 2. I told you earlier that they take a mean value of the ice core readings over 1,000 to 4,000 years. What happens when you take a mean value? Well, for instance, this is temperatures, could be anywhere in the United States, January through December. Average high temperature getting up to, in the summer, 90 degrees. Average low temperature, 66, 65. Now, what if you take a mean? What does a mean mean? Well, a mean is halfway between the low and high. All of a sudden, you've dropped that high figure by 17%. This is like the ice cores. Ice cores are on the mean. So 78% is your mean on here. Does that mean you've never been above 78 degrees in July? No, your average high temperature is 90, and you've probably had temperatures up around 100. That's what a mean does. Very misleading. So we have to do a correction to the ice cores. As I indicated before, they take this ice core sample. It may be a 1,000 to 4,000 year period. They only do one data point because they took a mean. One data point. There could be 20 global warming cycles in that period. But they took a mean value. The mean values eliminate spikes in the CO2 caused by global warming or volcanic activity, a lot of things. So here's the correction. We're going to add 17% to ice core readings. This is our peak values 425,000 years ago up to the year 1850. And the red line is 300 parts per million, they say, and it's etched in stone. Everyone says, we have never been above 300 parts per million. Never. You hear that all the time. Well, let's add 17% to that. All of a sudden, we're well above 300 parts per million. And this is just common sense, because when you take a mean value, you're going to squash that curve. And fossil fuel, all of a sudden, our curve is brought upward, and we lost a lot of the fossil fuel that they talked about. See that red line? Disappearing, a lot of the red on the right. And this is just common sense. You can't take a mean value and say that's etched in stone. We've never been higher than that. That's poor science. Another problem number 2 on ice cores, is I talked about new ice as compared to old ice. New ice is 5,000 years and newer. You can't use new ice. Reason is, in new ice, the air bubbles are not locked into the ice. Not yet. So during the first 5,000 years, you lose carbon dioxide back to the atmosphere. That's why we do not use new ice. But they don't tell you about this. So what happens, this is their ice core sample where they drill down. Here's the new ice. It's about 688 feet deep. And the loss of CO2, it loses 2.5 parts per million every 44 feet. So that means it's lost 30 parts per million during the first 5,000 years, back to the atmosphere. And they're not recording it in the ice core samples because it's not there. It's back in the atmosphere. So now what we have to do, here's our corrections for the 17% mean value. Now we have to add the 30 parts per million to it. Common sense. And look what that does. Wow. Back 425,000 years ago, we're way up to 377 parts per million, but we've never been above 300. And then that one jumps up. That one jumps up. Jumps up. And in 1850, 375 parts per million, all natural. But over to the right, they say, oh no, that was all industrial. So now we make a correction for that, and we bring that up. Now we're 88% natural on the carbon dioxide rise, only 12% fossil. Only 12% fossil fuel is in the total atmosphere. That's it. Way below what they're saying. Now, one additional research, which verifies what I just told you on these corrections, that's a plant leaf. Well, if you can find fossilized plant leaves, see, the leaflets have what they call stomata cells in it, like our lungs, little tiny lungs in there. If you have less carbon dioxide in the air, you have more stomata cells because it has to have help on getting the carbon dioxide. If you have a lot of carbon dioxide, you have less stomata cells. So what they did, they found fossilized leaflets going back 1,000 years. And this is more accurate than ice core because they can tell this 1 year to the next. So they don't have to take a mean value over 1,000 or 4,000 years. And that's what it looks like. Shows that back in 1000 AD, it was up to 400 parts per million, then it dropped down to 250, up to 325, dropped down to 235, then in 350, 360, 340, and then over there on the right is us. Now, a lot of people looked at this and they said, oh, it's too up and down, too up and down. Ice cores don't show that. The ice cores are nice and flat, so this can't be right. So a lot of people ignored this. But now let's take this. There's our global warming cycles the past 1,200 years. You can see those cycles again. Let's overlay the carbon dioxide from the plant stomata cells. Look at that, another perfect fit. You warm up, and the carbon dioxide comes up. Cool down, carbon dioxide goes down. And here we are over here in 2021. Carbon dioxide is, well, this is 2018. Most of the studies go to 2018. 375 parts per million. So you can see we're pretty much at the top of the cycle pretty soon. And when we go into a global cooling cycle, carbon dioxide is going to fall. It's going to fall quite a bit. So now let's put it all together. Total atmospheric carbon dioxide, natural and fossil fuel. My data, the two corrections I showed, put it at 378 parts per million. This is back at 2018 or so. The corrected NOAA formula by the physicists put it at 377, and plant stomata cells at 375. So this puts the fossil fuel at only 12% of the total atmosphere. That's it. All we have to do is use some common sense, if they're not doing it. I bet you didn't know that when they measure the carbon dioxide out in Hawaii, they measure the carbon dioxide and they tell you it's at 408 parts per million. They use a spectrometer to look at the air and pick out the carbon dioxide. But I did not even know this until the physicists showed me their paper. NOAA does not separate fossil fuel from natural. They don't separate it. The spectrometer can't do that. It can't tell the difference between carbon 12, 13, and 14. Those are 3 different carbons for natural carbon dioxide, fossil fuel, and also radiation and volcanic. They can't tell the difference. So they just tell you the whole value, and they say that's all fossil fuel. And that's not true. So what happened on how the physicists came up with this value, that it's only 12% of the entire atmosphere and 77% of the rise is natural, how they came up with this is, okay, NOAA doesn't have a direct measurement on how much is fossil, how much is industrial. NOAA uses a formula. That's how they do it. So they look at a formula on, okay, there's so much fossil fuel going into the air, so this formula will say, well, that's how much should be in the air. Well, the physicists found an error in the formula, a very simple error. And they're coming out with that on the paper, and that's going to prove that we're way up here instead, that the readings that we're being told about are not true. So all in all, fossil fuel, CO2, way too little to cause climate change. Do we have too much carbon dioxide in the air? They're all saying we do. Of course we don't. We've been up here before, about the same height. Let's see. Is 412 parts per million harmful? Well, in the greenhouses, they try to keep the carbon dioxide at 500 to 1,000 parts per million. Plants love it. It's fertilizer. When the dinosaurs roamed, the CO2 was between 1,000 and 1,500 parts per million. Way up there. Big, enormous animals, big, enormous plants. Everything loved it. Oxygen was 31%. Now we're down to 21% on oxygen. We're getting oxygen starved. And why? We don't have enough carbon dioxide. The plants take in the carbon dioxide and make oxygen. That's their byproduct. We need carbon dioxide to make oxygen. So past and climate cycles and future cycles. You recognize this again. This is the interglacial, very warm period back 450,000 years ago. And I've replaced the parts per million. It was up at 377. Then the next one, 378, 355, 375, 380, and our actual is 414. So 380 is natural, and 414 is the rest of that would have been the industrial. And actually, these figures that I have, 380, 375, 350, they could even be a few points higher. We do not know. So also, I told you about 8,000 years ago, we came off a glacial period. This is the glacial period back 10,000 years ago. This is 7,000 years ago, we were very warm because we're right on the peak of the interglacial period. Very warm, 50% less ice in the Arctic than today. You don't hear about that. No SUVs. And then there's other cycles. About 4,000 years ago, very warm, warm, warm. You can see it's cooling down during the past 7,000 years in all these cycles. And here we are over here. We're cooling down, not warming up. So here's our 230-year cycles that I was showing you before. We came off a global warming period This is back around 1000 AD or so. When we came off the first global warming period, it was 200 years when we came off the next global warming period. 230 years, we came off this global warming. 240 years, we went into global cooling. 230 years later, we went into global cooling. Now, 1794, year 1794 is when they went into global cooling. 1794 plus 230 equals 2024. We should be in global cooling. You can't stop these cycles. They are coming. Now, do we have any signals yet that it's coming? Winter of 2020, from Alaska through central Canada and Greenland, third coldest January and February on record. How can you have that during global warming? This year, the Antarctic winter just ended in September, the coldest on record. That global warming, I guess, is causing a lot of cold. The Arctic right now, in October, most ice in over 6 years. Global warming, there we go again. So, we're back to the proof of global warming. This is 1860, here's now. Well, up in the northern latitudes, they're putting the longies back on. And global warming will not end the world in 12 years. We know that. But we do have a problem. Don't clap too soon. We're almost done. The unexpected climate change disaster. Maybe you remember it from a couple years ago. I had the slide in there. There's our global warming cycles during the past 1,200 years. The yellow dots are historically strong volcanic activity. The last one was in 1815, caused the year of no summer in 1816, 1817. Killing frost every month of the summer from Maine to Virginia. Ice on small ponds in Pennsylvania in July. That occurred on at least 4 out of the last 5 global cooling cycles. 4 out of the last 5. And we're heading into a global cooling cycle now. This could very well happen in the 2030s. Back in 1815 and 16, we only had 1 billion people to feed on Earth. 1 billion people. 1/3 of Europe perished during the next 30 years from starvation, disease, and civil unrest. We have 8 billion people, may even be up to close to 13 billion people in the 2030s. If we have 1 or 2 years of no summer due to global cooling and a strong volcanic activity, 13 billion people to feed. We can't do it. Can you imagine the civil unrest? We could very well lose 75, 80% of the population just due to civil unrest and starvation at that time. And it's probably coming. Okay. That was the year of no summer that I talked about. Okay. That's it. Thank you. Now you can clap.